Hello everyone, welcome back. As you can see as of this recording, normally I would be doing CodeChef Starters 100 right now, but that contest might be sometime in late August. I figured that I may as well have some other thing to do during these weeks where there isn't actually a CodeChef Starters contest, so why not, let's go. I was thinking I might as well do a practice contest of some sort. So here we have the very first Starters contest. Starters 1, February CodeChef Starters 2021. This was back when the problems for Division 3 were the same as problems for Division 1. There were just these 6 problems. And I figured we may as well just go through these and we can do this practice contest kind of like if it was an actual normal contest. So here I have the timer set to 2 hours, and once I press go here, I will be running through as many problems as I can here. 3, 2, 1. Alright, here we go. Okay, so we got our first problem, chef and coupon. So let's see here. We got food from a food delivery app. There's 3 items. He'll also order once tomorrow with 3 different items. And there's a delivery charge of D for each order. So there's also a coupon. If he buys the coupon, delivery charges are waived. So only need to buy the coupon once to waive the fee on both days. Okay, so let's look at our input. We have our base input for I in range, int, fixed typos here. So these are delivery charge, these are coupon cost. It might have been easier to read those values in an array and just take a sum, but oh well. If A0 plus A1 plus A2 is at least 150, I think. Let's just look back up here. Then the delivery charge is waived. So V will be the amount of value we get from buying the coupon. V plus equals D. And then we do the same thing with the second day. And if V is greater than C, he'll buy the coupon only if it costs him strictly less than what it costs him without the coupon. Then has to be exclusively less. So pretty much if the coupon was like costing 80 and the amount you save from delivery fees is also 80, then it should still be no. Okay, let's run here. Yes, and then no. Oh. Maybe bring this up a bit so I don't accidentally bring that bar up. And there we go, first correct answer. Okay, we're gonna go to the next one now. 436. So we got college life 2. There's S seasons. Each season has some number of episodes. Each is some number of minutes long. They all include the duration of the beginning intro song. And intro song changes slightly each season, so we'll watch the intro song in the first episode each season and then skip it in the rest. Find the total number of minutes. Okay, this is... I think this should be fine here. So, S is the number of seasons. Then... Okay, wait a second here. First line of each test case is the number of seasons. Second line is... Second line contains S-based integers. Duration of the intro song, so we'll put it as IL. Second one contains S-spaced integers, which... no, wait. Then it will contain EI plus 1 space separated integers, where the first integer is EI, denoting the number of episodes, and then each of the episodes. Okay. So answer is 0 for J in range S for number of seasons. AR is containing the information about our current season. The total length of this season is just the sum minus the first value, since that just tells us the number of episodes. And to also account for intro length decrease. So we watch the intro in the first episode, but then everything else we can skip that. And the intro length is from IL J. Lastly, increase answer by total watch time length. Print answer. Seven. Okay, nice. Very nice. So now we'll go to our third problem. Let's see, 850. M value, maximum value. So, okay, this looks a very simple problem. Given an array size n, so A times B plus A minus B. A and B are two distinct elements of the array. Okay, also to note here is that we can have negative values. Okay, for obvious reasons we can't do ends. we cannot just brute force this because that would just be an n squared solution, and n is at least 100,000. So let's make a note here. O n log n minimum in performance. Okay. We just have to choose two distinct elements. So immediately one thing I'm possibly thinking is that a sort might be useful here. Then what I'm considering is something like this here. So clearly let's say we just take our two highest and two lowest values. I don't know if they're going to be positive or negative sort of things, but let's assume that we have an incredibly high positive value or negative value here. Like, so this way, these ones represent A, and these ones represent B. So if they're both positive, then A times B is positive. Then it's just a difference between A and B. Just choose the larger of the two to act as A or B. So then this has to be positive. The negatives, it's basically the same thing as, well, there, because you can still get a very large positive. Like if you have negative 500 and then negative 1000, the multiplication should be positive. And then you just do like negative 500 as your plus, and then minus, and B would be negative 1000 to get another plus amount. But then we get positive negative cases here. 1 second.
Hello.
Hello, Amanda.
You can't have to check the car.
Okay, very cool. I continue my
Yes.
thing.
You do your own thing.
Okay, now where were we? Positive minus. Thing here is, if we do positive times negative, we get a negative, and maybe we can do a double positive. And yeah, you could set up a double positive, but it's addition. That's the thing. So, in most cases, this will be negative, and same thing here. We either want two largest or two smallest values, most likely. What about... Now the question is what happens if it's a case like... Let me see here. Where is it? What's the constraints here? Yeah, we could have a bunch of zeros. That's where things get really weird. Because what if you have something like negative 1, 0, and 1? Or you have two of each. What's the best setup there? Because 1 and 1 you get 1. 0 and 0 is 0. The 1, 0 cases you also get 1. Okay, then that leaves -1 and -1 you still get 1. -1 and 0 you still get 1. And -1 and 1 you still get 1, because you multiply that you get -1, but then you can do 1 and then -1. Yeah, maybe it is just largest and smallest values. So A times B, ABS A minus B. If B is larger, we'll just flip it to positive if needed. Yeah, this problem is definitely a little bit trickier. And runtime of this would... I mean, the sorting makes it then log in, but there's probably an ON... Yeah, there's ON solutions. So this is actually the correct method. Interesting. Okay, then I guess we're going to the next problem here. So far, everything's looking pretty good. Okay, we have valid string as our next problem. 15:38 in recording, and 15 minutes have passed. Okay. I mean, we can tell by the difficulty rating it's going to slowly increase. We have a binary string. There's a right circular rotation. Is there a right circular rotation of the string? So every two adjacent ones are separated by a mostly zeros? Okay, what? So right-wise circular rotation means that like we can pretty much start from any point of the string. So stuff like 011001. So we can rotate it so that if we start from the second last character, then it's also possible to get 01011100. I mean, either way, it could also be leftwise, it should be the same thing. We get 2 lines of input. Okay. NC is the first line. And then we'll do an input here because actually reading the integer will cause some very shenanigan-y stuff to occur. So every 2 adjacent ones are separated by at most C zeros. So that's a 1. Six circular rotations of string. Okay, so pretty much we want the gap in between every single pair of, like, every adjacent ones. So in this case, this string normally has a gap of 2. Okay, so what we can do here is we can actually set up a case of removing the largest gap here, because we see this largest gap. And what we do is we rotate it until all of these zeros are at the end. So then they're not actually creating like a new gap in the string, since there isn't a 1 afterwards. Yeah, let's try something like that first. So our gaps will be in a list for j in S, and we need to track how many zeros we run into. Happen chain equals 0, rwise Now if we have a massive string of zeros at the end, then we still need to account for that, so chain sorts here. And we can disregard largest gap due to rotation. So one thing to note is if we have a string of all zeros, then this is going to then this list will be empty. And either way it's going to be a yes. Otherwise, we take the largest value. If it is at most C, then it's still yes. I have to fix my input here. Oh, for God's sake. Okay, let's see. Okay, so apparently we can just copy and paste it here. The frick? Okay, fine. We're going to do something like this here. So that's a yes. Okay, it's still given yes. Okay, never mind. We have an issue here. Oh wait, yeah, this has to be 0. Yes, no, yes, there we go. Okay, we got wrong answer. The last case is correct. Just to make sure we know why a circular rotation is. Yeah, that looks like a... Okay, so our circular rotations are probably fine here. Oh, I see what's going on here. We're not actually setting up the gaps correctly, because we could be getting 0, 0, 0, 0, 1, 0, and then some random stuff here, and then a string of zeros. What will end up happening is you track these 4, and then you track the last bit. Okay, so what we actually want to do here is we want to set up an increment. While increment is not equal to n, if s increment, if we're starting on a 0, then that way we continue until we start on the 1, so we get all of the chain links correct. If we somehow have increment equal to n, then everything is a 0. We do a print yes and just continue, so we don't have to do everything else after. And make sure we have break statement to get out of the loop. So we'll do like 9 1 0 0 1 4 5 6 7 8 9. Yeah, that looks about right. Previously, I'm pretty sure that gives a no. There we go. Yeah, that was a good run. That's very good. Okay. Looking at the solve rates, this is the point where things are going to get a lot harder. So we got college admissions, and looking at our problem, we have n colleges ranked individually. They have a single seat. You have to give a common exam result. Every student does a common exam. And then from highest to lowest rank, chooses the college of their preference list. Each student has a list of colleges. You get the information of M students. And you try to get into the highest ranked college. If it's not on there, then don't join, okay? Okay, let's handle the input first, because this is a little bit tricky. We get our input. Have N and M. So we get our college ranks there. And then the next M lines so we get student ID and preference rank. So next, M lines contain k plus 1 space separated integers, where first integer k is the number of colleges. So let's just make one more note. Student ID 0 is number just in list. Okay. So N and M can be up to 50,000. There are some number of test cases, but then some of N is at most 300,000. Okay, so let's figure out a few more things. A few more things is M could be more students than colleges. Clearly, we can't just emulate the entire process here. At most 1.5 mil preferences. And that might be the clue here. Seeing that we have at most 1.5 preferences. Like, it's very tempting to do something with N and M and try and do a very janky solution there. But I think O of K might be the answer. What you do here is pretty much make a list. You put in, make a list of tuples, which is so exam rank first, then preference of college, you put in student ID and their college ID as well. So only if bin and student is open. Number of students. Okay, yeah, this is kind of really scuffed input. If we're looking at okay, so our first test case is here. So Jeff is the first student every time. This is his preference list, so he's applying to college 1-2. So he's applying to the college with rank 1 and rank 2. Hits rank 1, and that has ID 2 from the previous list here. So that's why we put 2. The next one is a 0. Since there's only 1, then there's ranked 2nd. And then the third one. Okay, the third one, it's 1 and 2. It applies to college 2 and 1. Okay, at the very end, we can figure out what college did he actually go to. So we'll do something like this: O times n plus 1 . And we need one more. So we update this to college rank, student ID, yeah, we'll change the IDs for the students from 0 to n-1 just for convenience. So for every student, K will be at least, well, K be at least 1 every time. Either way, there should be at least 1 K. For Ellen range, CRK 1, 2. Now we need to put in the tuple. So we need exam rank, college rank, and student ID. Firstly, student ID is just K. So K is the student rank and choices. The college rank is CRKL. And then lastly, we need the scores, the student ranks, BRK for student ranks. This puts the first students in front. Okay, so now for E in choices. P1 and P2 are needed. P2 is student ID and then college rank ID, but I'll call it college ID. So if college SID is 0, or college here is -1 because we might use 0. And student is not currently going to a college. And we repeat through all of this. We just keep going here, and we find the intended ID. Two, 0, and 1. Okay, yeah, I think it's... Oh wait, and we want... Oh, so now we want the IDs of the... Okay, so yeah, so this is really just implementation hell. So what we've done here is we put in the ranks of students rather than the actual IDs. Okay, it might be best that we include a dictionary here. To translate the college ranks into dictionaries. So we need ID, so ID will be just the index in the list plus 1 will be equal to so then here we have exam rank, and we need to get the college rank. And student ID there. Alright, that's very good. Okay. Well, we got one more problem. Didn't think it'd get this far, but right now we try the last problem. F. F, 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 F. Okay, where is Chef in divisors? It's 4810 now. And we go to our final problem, this contest. You have an integer n, you can apply an operation on n some number of times. Positive integer k. K has exactly 4 divisors, and k is a divisor of n. And then n goes to n over k. What's the minimum number of divisors possible from the resulting number n? So a positive integer k has to divide n. And then n has to be n over k. How many divisors are remaining in the resulting n? Okay, the first really big clue is exactly 4 divisors. If we think about it, a prime number only has 2 factors, one in itself. Now if you take 2 different prime factors, x and y supposedly, then its factors are going to be 1, x, y, and xy. That will always work. But then we have to be a little bit careful because there are a few other scenarios. So like xy, you get 1 x, y, and xy. I think x cubed is also another thing because you get 1 x, x squared, and x cubed. You can't have 3 different prime factors. That will give at least 8 different setups. Or more than 4 for sure. There's up to 1 million cases, and n can go up to 1 million. We also have a few other subtasks. Okay, well, and never mind. Yeah, 64 is 2 cubed twice. That gets us to 1. 30 is 2 times 3 times 5. We can only remove 2 of those. 120. We can do 2, 2, 2, 3, 5. 45, you get 3, 3, and 5, so you'll end up with 3. This is a bit tricky here first. Okay. Get that. Yeah, I think first thing we got to do is we have to find what the primes are. That'll be pretty useful first. Where is it? What we need to do for this is probably the fastest way is just using this simple scythe. For J in range, if it is true, then we'll do a Okay, so we have our scythe. So primes equals scythe up to a million. And then yeah, 78,498. Might be a bit of an issue here. But the thing is that is it actually that long? Okay, so we can Okay, there actually might be a way we can just label every single value here. So we can set up a 1 million value array. So we tracked all the x, y's, and x cubes. And then let's say we call this dz. Z is our value we're testing. It's going to be one of a few cases. Either it's prime, so then that'll be its answer 2. If it's 1, its answer is 1. If it's a square of a prime, its answer has to be 3. And if it's not one of those, then it has to be divisible. So then it has to be divisible by one of these two, because either you get p cubed or you add a different prime factor, then it has to be divisible by there. Div and continue. There is also something really tricky we have to look out for, which is 2 cubed times 3, the 24 case. In this case we want to take the cube, but there's also 2 times 3. So do we fill in cubes first? The answer is not always, because then you can also get 3, 5, 7. Then you want 2, 3, 2, 5, and 2, 7. So the value can be at most 3. Forget 1. Okay, we are only going up to 1 million. We could also just take the prime factorizations. Okay, that that actually sets up another question. How many cases of triplets do we even have to test? What is the highest number of triplet cases that we actually have to test? 2 cubed times 3 cubed times 5 cubed. That's already 27,000. You add in the 7 cubed. You're already at 9 million. So then you could have up to 3 choices. 6. There's actually only 12 choices. There's at most 12 choices possible. And really it's more like 16. So first you can find the prime factorization. If there's any triplets you want to remove, then you remove them. And you generate as many pairs as possible. Because you can always get something like 2, 3, 2, 5, 2, 7, 2, 11, 2, 13, 2, 17. That is a possible setup, right? That's actually too big. 3, 4, 5. Okay, let's first we need to adjust this to a factor size. If it's 1, then there will only be one factor. If it's a prime value, we can't do any better. And then, so I guess now what we're doing is we're making a dictionary to store the frequency of each factor. So that'll be just the first prime that divides. And now we have to interpret the factors. So factor count will be 0. Factor highest will also be 0. I in factors dot keys. Factors I is greater than or equal to 3. Then we need to do a variant with the triple removal. I'm not sure how we'll store the answer, but we'll just divide by I to the 3 times j and primes so we don't have to do multiple and this could be a bracket. Most likely it will be just one case, but could be multiple. So factor count is increased by and the most number of factors is maximum of factor in frequency. Pairs is minimum between factor count hard slash 2 and then number of factors minus the highest. So like if we have 10 total factors but there's 7 of the highest one, then we're only going to be able to make 3 pairs because you have 7 2s at 3, 5, and 7 sort of scenario. Then those 2s would have to be removed in a triple, but we're not including triples for now. And clearly if we have like a very balanced setup, we can't just make like 9 pairs out of 10 numbers. Pairs times 2, factor count minus pairs times 2 so in that way if we have like pair plus 1 minimum of answer and this two, 3, 4, 5, 6. Okay. I'm very sure this implementation here is yeah, wait, this implementation here is definitely suboptimal. Because if we consider it with 2 to the 12, for instance, 2 to the 12, you can get 2 to the 9, 2 to the 6, 2 to 3, and 0. That's what it will generate out of there. The 3 will also generate a 0. This will generate a 3 and a 0, which generates into a 0. This generates into a 6, 3 and 0. This generates to a 0. This generates to 3, 0, and 0. Like just from here alone, you get 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I don't know. It might be. Yeah, I'm doing some sort of. Maybe if we only do one triple, so we basically do a. But then you get like 2, 3, 5, 7, 11 cases once again. Yeah, I think it's. We'll do testable values equals. This will be our testable value list. We have to do this initially once. Factors, while primes, and none. We don't need any of these now. If frequency is. For j in range, so I to the 3 times j is our divisor. So we may as well just figure out what values could we even get. So div equals I to the exponent 3j for k in range, or for k in current AR, br.append k divided by div. Oh yeah, we also have to consider that we could just get the same. We could just ignore these. From copy, import deep copy. Or we can just do divide by 0 and it's there. Reset AR to be BR. For S in AR. Answer equals min, answer and F. Ask what primes. Goes through all of this again. Don't think we need this anymore. We're not considering frequencies any longer, since we're going to be testing every single value correctly. It'll be answer is just going to be the number of factors minus pairs times 2. It's 1, which is just over here, and return this instead. Okay, sieve is not found because we need F sieve. 5, 3 gives there, 64. X not defined. Line 53. Yeah, we don't need N anymore, do we? Frequency is not defined now. Yeah, we still need to include there. Oh, we didn't do a current answer. 5, 3, 64. Okay, that's already our first sort of issue. There. I think I might know what's going on, but so just print AR. If X is 1, three, okay, 64. Does 64 and 8. Frequency divided by Ah, it's only counting up to 5. Yeah, while primes... not... Yeah, then we still need to do... We still need to do this one more time here. Because we'll be on the prime factor. Five, 3, 64. Now we should get... Okay, that's... Oh, how is this being implemented, the F side? If it's equal to 1, I is prime. Wait, 2, 4, 2, 4, 8, 16, 30. What? If factor is getting n is none, then we need to oh wait, no, this is a prime. At this ending stage, it should be a prime, so we do n instead of this. 5, 3, 64. Okay, now I'm thinking there's probably going to be a... Yeah, there's a different problem now, is there? Because if I'm having that sort of issue, then we need to factors dot get n equals none factors this way we should be getting the correct number of factors occurring. 2, 1, 2, 1, 2. Okay, let's try something like this here. We going 6 for 6? Let's go, we got all 6. And that concludes Starters 1. A perfect run. Excellent. Very much we just want to find prime factorization. The triplet strategy works where you just like brute force every possible case of removing triplets because you can only have so many different combinations, because I think you take 2 cubed, 3 cubed, 5 cubed, 7 cubed. Like, you can't really do it until... So, like, for instance, if we did if we took the cubes of 2, 3, 5, and 7, and 11, this is already well over a million. I think these are equivalent, right? Yeah, even with just the first 4, that would get you over a million. And it's like, if you do either you divide by 2 cubed or you don't sort of case, that would only result in 16 cases. So there isn't actually many triplet cases to consider. The rest of this is pretty much log n from, like, each test case then runs in log n due to how factors work. And that basically sums up this entire contest. I'm honestly a bit surprised that somehow I got all the questions in this contest, but this is also like back when this is back when Starters was only rated for Division 3. For all I know, maybe in the later contests when they made it rated for Divisions 2 and Divisions 1, that's when they started adding even like much trickier problems. But yeah, I will be real. This is 2900 difficulty rating feels a bit high here. This didn't really feel like 2900. Maybe 2500. Like this is still a pretty difficult problem with multiple steps, but it isn't like impossibly difficult, out of my range difficult. But yeah, yep. That is all for this contest, even though there is 24 minutes left. And who knows, maybe next week I will do Starters 2 as a practice contest while we still wait for whenever Starters 100 will happen. In that case, I'm going to be going now. See you all next Wednesday. And yeah, have a great day, I guess. Yeah, take care.